Parents spend over $600 on products labeled STEM and watch their kids walk away with nothing that translates to a real job skill. Not a line of actual code they can use, not a design file they can print, nothing. I'm Rajiv Patel, and after 15 years watching which technical skills actually get candidates hired versus rejected, I put together a framework that filters out the noise and shows you exactly how to choose products that build career-ready capabilities, instead of just filling up your garage with expensive plastic. You're listening to the STEM Lab podcast. Quick heads up before we get rolling. Everything you're about to hear, the research, the data, the framework, that's all human verified and written by a real author with 15 years in the field. The voice delivering it is AI generated, just so you know what you're listening to. If you've been tuning in for a while, thank you for being here. If this is your first episode, welcome aboard. We drop new episodes every Monday, Wednesday, and Friday. And today, we're tackling a problem that costs parents a fortune. How do you actually choose STEM products that teach skills companies hire for, instead of just toys that get tossed in a closet after 3 weeks? Let's jump into it. This guide is built around a systems-level framework for evaluating STEM products based on technical compatibility, progressive skill acquisition, and alignment with what companies are actually hiring for. You're looking at about 45 minutes to establish your evaluation criteria, then you apply it ongoing across every purchasing decision. I ran my own kids through these filters after we burned through that $600 in products that delivered zero employable outcomes. The methodology I'm sharing comes directly from observing which entry-level competencies consistently separate hired candidates from rejected ones over the course of my career. Before we get into the steps, here's what you'll need to have ready. First, a current learning path audit. You need to document where your kid actually is right now in programming logic, mechanical systems, and circuit fundamentals. Second, a platform compatibility checklist. What operating systems are available in your household? Windows, Mac OS, Linux, Chrome OS? What mobile devices do you have? Do you need offline capability? Third, budget allocation framework. What's your total STEM investment capacity across 12 to 24 months, including consumables and subscription costs? Fourth, space and power infrastructure assessment. What workspace do you actually have available? How many outlets? Do you have ventilation if you're dealing with thermal processes? And fifth, an industry skill taxonomy. This is a reference list of actual entry-level job requirements from current postings in robotics, software development, manufacturing engineering, real job descriptions, not marketing fluff. All right, let's start with step 1. Map product capabilities to industry-standard tools. How you choose STEM toys that teach real skills starts with reverse engineering from professional toolchains. A product only merits consideration if it creates transferable competency in platforms actually used in employment contexts. Here's how you evaluate each product against technical progression. Block-based programming like Scratch or Blockly, that's an entry point only. The product must explicitly support transition to text-based languages within 6 to 12 months. Python is the industry standard for data science, automation, AI, and ML applications, so prioritize products with Python API access. Arduino IDE and C++ form the embedded systems foundation. This is essential for robotics and IoT career paths. CAD software compatibility, whether it's Fusion 360, Tinkercad, or OpenSCAD, signals genuine design skill development. And for advanced products, look for version control exposure. Do they introduce Git concepts or collaborative coding workflows?
Take the LEGO Mindstorms Robot Inventor. Check the link below to see the current price. This demonstrates clear value because it supports Scratch for initial programming, then Python for advanced users. You're preparing learners for the same environments used in university robotics labs. Contrast that with closed ecosystem products that lock users into proprietary languages with zero external application. Products teaching coding through narrative games without exposing actual syntax, logic structures, or debugging tools fail this filter immediately. You're purchasing entertainment, not skill development. Moving to step 2. Verify progressive learning architecture. Career-ready skills build through sequential complexity, not scattered exposure. You need to evaluate whether a product exists within a documented learning path that connects foundational concepts to advanced applications. Here are the essential path components you're looking for. First, input-output fundamentals. Sensors reading environmental data, actuators responding to programmed commands. Second, conditional logic. If-then structures, Boolean operators, state machines. Third, variables and data structures, memory management, arrays, basic data types. Fourth, functions and modular code, reusable code blocks, parameter passing, return values. And fifth, hardware-software integration, understanding how code translates to physical behavior through electronics. The Vex Robotics V5 Starter Kit exemplifies this approach. Check the link below to see the current price. Each build increases mechanical complexity, while programming challenges scale from simple motor control to competition-level autonomous navigation. The system supports learners from age 10 through high school, eliminating the need to abandon platforms and restart skill acquisition. Products without explicit skill ladders, those presenting isolated activities rather than cumulative competency, deliver no lasting value. Understanding how screen-free coding prepares kids for text-based programming provides a framework for evaluating these progressions across different categories. Now, step 3. Assess technical compatibility and lock-in risks. Real-world engineering demands tool interoperability. Products that create vendor lock-in or impose artificial compatibility restrictions teach the wrong lessons about systems integration.
Here are your critical compatibility checks. Operating system requirements first. Does it function across Windows, Mac OS, and Linux? Cloud-dependent products become unusable when internet fails or services shut down. Prioritize offline-capable solutions. Hardware expandability is next. Can you integrate third-party sensors, motors, or components? Proprietary connector systems that prevent standard electronics integration limit advanced learning. Software licensing matters. Does the platform require ongoing subscriptions? Annual fees for basic functionality represent poor ROI compared to one-time purchases with perpetual access. And file format standards for CAD products. Does it export to industry formats like STL, STEP, or IGES? Proprietary file systems trap designs within single ecosystems. I eliminated 3 robotics platforms from my children's lab after discovering they required cloud connectivity for basic programming. That's unacceptable. Internet outages shouldn't halt learning. The Arduino platform remains standard specifically because it's open source, runs offline, and accepts any USB-compatible sensor on the market. Step 4. Quantify skill outcomes with capability milestones. Vague age recommendations like ages 8 to 12 provide zero useful information. You need to demand specific, measurable skill outcomes tied to completion of product activities. Acceptable capability milestones look like this. Student will program a 3-sensor decision tree using and/or logic operators, or learner will design, slice, and print a functional gear train with specified torque characteristics, or user will train a supervised learning model to classify images with greater than 75% accuracy, or builder will construct a PID-controlled line-following robot from individual components. These outcomes map directly to competencies evaluated in technical interviews. Compare this specificity to marketing language like explores coding concepts or develops problem-solving skills. Those are meaningless claims that excuse poor instructional design. Products achieving these outcomes prepare learners for STEM skill milestones that 10-year-olds can actually master, creating competitive advantage when applying to selective STEM programs or university admissions. On to step 5. Calculate true cost, including consumables and expansion. Entry price represents only the first data point in total cost of ownership. How you choose STEM toys that teach real skills requires analyzing the complete financial picture across the product's useful learning lifespan.
Here's what goes into total cost analysis. Subscription requirements can add $120 to $300 annually. If you're looking at a 5-year product lifespan, that's $600 to $1,500 in hidden costs. Consumable expenses matter too. 3D printer filament runs $15 to $25 per kilogram, and active learners consume 2 to 4 kilograms monthly. Electronics kits with non-reusable components require continuous restocking. Expansion modules are another consideration. Does the product provide 12 to 24 months of learning, or does it require $50 to $150 expansion packs every 3 to 6 months to maintain engagement? And replacement parts for durability. Products with fragile gears, brittle connectors, or proprietary batteries that fail within 18 months represent poor long-term value. The Creality Ender 3 V3 SE 3D printer demonstrates transparent economics. Check the link below to see the current price. $200 initial investment, $20 a month in filament for active use, no subscriptions, widely available replacement parts. Contrast this with subscription-based coding platforms that charge $30 a month for content that becomes inaccessible the moment you stop paying. Calculate cost per skill hour, total expenses divided by documented learning time. Products exceeding $5 per meaningful learning hour rarely justify their price. Step 6. Evaluate lab specs for educational environments. Consumer toy standards differ fundamentally from educational equipment requirements. Products entering a home STEM lab setup must meet infrastructure and durability specifications. Here's your lab specs checklist. Power requirements: voltage, amperage, outlet count. This is critical for spaces with limited electrical capacity. Battery-powered products need documented runtime and recharge cycles. Connectivity matters. USB 2.0 versus 3.0, Bluetooth version, Wi-Fi requirements. Legacy USB 2.0 creates bottlenecks for data-intensive applications. Physical durability includes drop test ratings, component replaceability, UV resistance for window-exposed labs. Consumer-grade plastics typically fail within 12 to 18 months of daily use. Thermal management is next. Does it require ventilation? 3D printers and soldering equipment need airflow specifications. Products generating fumes demand exhaust solutions. Noise levels. Decibel ratings matter for shared living spaces. Some 3D printers and robotics motors exceed comfortable background noise thresholds. And storage footprint. Dimensions when stored versus operational space requirements. Products requiring permanent desk space compete with other learning activities. Products lacking published specifications for these parameters signal consumer-grade manufacturing incompatible with serious skill development. Home STEM Lab safety requirements provides a comprehensive infrastructure checklist. Now, Step 7. Verify alignment with hiring trends and skill gaps. The 2026 employment landscape shows clear skill deficiencies in entry-level candidates. Products addressing documented gaps deliver superior career preparation value. Here are current high-demand competencies with insufficient candidate supply. Python for automation and data analysis. 67% of entry-level data analyst positions require Python, but only 23% of applicants demonstrate proficiency according to the Stack Overflow 2025 survey. CAD for additive manufacturing. Design for 3D printing represents a growing manufacturing segment, but most engineering graduates lack practical experience with toolpath optimization and material properties. Embedded systems programming. Arduino and Raspberry Pi skills appear in 41% of junior robotics engineer postings, yet remain absent from most computer science curricula. And machine learning implementation. Not theoretical ML mathematics, but practical model training, dataset preparation, and inference deployment using TensorFlow or PyTorch. Products teaching these specific competencies position learners ahead of peers pursuing generic STEM enrichment.
The Raspberry Pi 5 starter kit addresses multiple gaps simultaneously. Check the link below to see the current price. Python programming, Linux exposure, GPIO-based hardware control, and preparation for cloud computing concepts all in one platform. Understanding which programming kits build actual coding skills helps distinguish career-relevant products from coding-adjacent toys. Final step, Step 8. Test against real project requirements. Here's your final validation question. Can the product support an actual portfolio project demonstrating employable competency? This question eliminates products with impressive marketing but insufficient technical depth. Portfolio project criteria look like this. Complexity threshold first. The project must require 20 to 40 hours of focused work, integrating multiple concepts learned across product use. Tangible output. You need a physical prototype, working code repository, or documented design file, not just completion of guided activities. Presentation readiness. Results should be suitable for science fair exhibition, GitHub portfolio, or college application supplement. And iteration capability. The product supports debugging, redesign, and optimization cycles that mirror professional development processes. Products passing this test enable learners to answer the interview question, "Show me something you've built," with concrete demonstrations of competency. Those failing produce only guided activities with no creative application.
I evaluate this by attempting to use each product to solve an actual engineering problem I've encountered professionally, scaled to appropriate complexity. Products that can't support this translation lack sufficient depth for skill transfer. Let me share some pro tips and common mistakes. Avoid age range marketing. Chronological age correlates poorly with skill readiness. A 12-year-old with 3 years of block coding experience needs different products than a 12-year-old starting from zero. Evaluate based on current demonstrated competencies, not birthdays. Age-specific STEM learning paths provide better frameworks. Prioritize products supporting failure. The most valuable learning occurs during debugging and troubleshooting. Products that prevent failure through excessive handholding teach learned helplessness rather than engineering resilience. Look for platforms that expose error messages, allow incorrect approaches, and require systematic problem solving. Recognize when to abandon platforms. Products serve specific skill ranges. Continuing to use entry-level tools past their learning ceiling wastes time better spent advancing to professional-grade platforms. Plan transitions before purchasing. Know what comes next in the learning path. Discount entertainment value. Engagement matters, but fun frequently masks shallow learning. Products emphasizing game mechanics over skill acquisition optimize for the wrong outcome. Some friction and challenge signal genuine learning is occurring. Here's a common mistake. Purchasing multiple products teaching identical competencies at similar levels. 3 different block coding robots don't accelerate learning. They represent redundant investment. Instead, build vertical depth through progressive complexity. I maintain a spreadsheet tracking skill acquisition dates, capability milestones achieved, and time investment per product. This data reveals which purchases delivered ROI and which represented wasted capital. Verify that the product uses or directly connects to software and hardware platforms employed in professional contexts: Python, Arduino IDE, Fusion 360, Git, standard electronics components with datasheets. Products creating this bridge explicitly state compatibility in technical specifications. Those using proprietary languages, closed ecosystems, or unique hardware with no external applications prepare learners for nothing beyond that specific toy. Research whether universities and companies use the same or directly related tools. If not, the product teaches a dead-end skill. Should I choose products requiring subscriptions or one-time purchases? One-time purchases deliver superior long-term value unless the subscription provides continuously updated curriculum explicitly teaching new industry-relevant skills at rates faster than the subscription cost. Most subscription models lock away basic functionality behind recurring fees while delivering static content. Unacceptable economics. Calculate 5-year total cost and divide by estimated skill hours gained. Subscription products rarely compete with purchase-once platforms on this metric. Exceptions exist for advanced cloud computing platforms teaching DevOps or distributed systems concepts that require ongoing infrastructure costs. How many STEM products should a child have at each skill level? One comprehensive platform per skill domain at each level. One robotics kit, one programming environment, one design fabrication tool. Multiple products teaching identical competencies at similar complexity levels waste resources without accelerating learning. Budget for depth through expansion modules and advanced challenges within platforms rather than breadth across redundant products. The transition point to a new platform occurs when the current platform can no longer support meaningfully more complex projects, typically 12 to 18 months for quality platforms. Progressive STEM learning paths should stack vertically, not horizontally. Let me summarize what we've covered. How you choose STEM toys that teach real skills requires systematic evaluation against professional competency requirements, not marketing claims. Prioritize products exposing learners to industry-standard tools, Python, Arduino, CAD platforms, through progressive skill architectures with documented capability milestones. Calculate total cost, including consumables and subscriptions. Verify technical compatibility and expandability. Assess lab specs for educational durability. Products must support portfolio-quality projects demonstrating employable skills, not just guided activities with no creative application. The framework eliminates 80% of products marketed as STEM by revealing their lack of transferable skill outcomes, poor technical architecture, or unsustainable economics. What remains represents genuine investment in career readiness rather than expensive entertainment. I apply these filters to every product entering my children's learning environment, accepting that fewer, better chosen tools deliver superior outcomes to larger collections of shallow alternatives. Deploy this evaluation methodology before your next purchase. The difference between toys and tools is measurability. Real skills produce quantifiable capabilities that translate directly to competitive advantage in academic and employment contexts.
Thanks for listening to this episode of the STEM Lab podcast. New episodes go live every Monday, Wednesday, and Friday, so you'll never have to wait long for the next one. If you got something out of this episode, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It's honestly the biggest thing that helps other parents and educators find the show when they're searching for this kind of content. And if you haven't already, hit subscribe or follow so you get a notification the moment a new episode drops. Appreciate you being here. Talk soon.